And hi everybody, this lecture 21 in quantum mechanics, and my name is Chris Collison, starts to explore a little further some spectroscopy associated with rotations. And now we start to think about how rotations actually take place on top of vibrations. So we're going to refer to section 6.3 of the textbook in here, and this particular section is titled Rotational Transitions Accompany Vibrational Transitions. And as I said, this is more about spectroscopy. So if we think back to chapter 5, we recognize that with vibrational motion, we have the harmonic oscillator. For rotational motion, of course, we have the rigid rotator. And so really when we think about it, we have maybe a diatomic molecule, maybe something with a permanent dipole, such as hydrogen chloride in the gas phase. And so we're going to combine these two ideas to think about that diatomic molecule. And we're actually going to call this the rigid rotator harmonic oscillator. So if we think about the eigenvalues that we get for the Schrödinger equation for each of those particular pieces, the rigid rotator and the harmonic oscillator, well, of course, we get our energies here in terms of the vibrational frequency. We have our quantum number V. And for the rotations, we've just talked about how the energies of those rotations are equal to the rotational constant in here, which is equal, of course, to h bar squared over 2I is that rotational constant. And that's multiplied by this term that we have in here with the rotational quantum number, J multiplied by J plus 1. So let's think about what that equation might look like, again, remembering that we're working typically in wave numbers in here. So when we think about how to convert to wave numbers, we're going to recall the equations here on the left-hand side. So remembering a quantized expression for a photon. So E is equal to h times nu. Lambda, of course, multiplied by the frequency is equal to the speed of that electromagnetic radiation. So lambda equals c divided by frequency. And if we take the reciprocal of this equation, then we end up with 1 over lambda, which is really our number of wave numbers. It's an expression of energy, and that's equal to the frequency divided by the speed of light. So of course, when we convert this now into wave numbers, we've seen this in the previous chapter. We end up with v plus 1/2. Effectively here, we're dividing throughout by Planck's constant, and so this is, this happens in this particular expression in here. It's kind of embedded in this particular equation. But we're also going to, of course, divide by c to get those wave numbers, right? So we get our frequency, by dividing the energy by Planck's constant, and then with the frequency we divide that by c in order to get our wave numbers in here. So this is the expression for the vibrations. Of course, the vibrational the rotational constant in wave numbers, as I mentioned earlier, was simply equal to h squared over 2 times 4 pi squared times I. So again, we remove one of the h's by dividing by h and then divide by c, and we end up getting this rotational constant in wave numbers. So what's the point of this? The point of this is really to look at the relative sizes of the vibrations. So a vibration is typically on the order of magnitude of about 1,000 wave numbers. And the rotational energies, the transition between rotational states, is about 1 wave number. So if we recognize that a transition might include a vibration and a rotation, then we're going to start to see, here's our vibrational energy curve in here. We've got our vibrations in here, and we're starting to see in here these individual rotations that are about 100 to 1,000 times smaller in size, that are going to sit on top of the vibrational energy levels. So I'm kind of confusing things in here with the red lines, but this is kind of what we see. We've also got to remember our selection rules in here. So remember, if we're coming in with light and we're exciting from a lower vibrational state to a higher vibrational state, then delta V in here is equal to +1. And we've also got these selection rules now for rotations, and we're recognizing that delta J is going to be equal to ±1. So what does that look like? So it turns out this is what happens, right? So this is let's perhaps say this is V equals 0 and V equals 1 over here, and what happens with that selection rule? So we go we have a +1 change in V, but we've got effectively two branches here, and the branch on the left hand side, and I should probably put this in blue. So on the left hand side here, we've got vibration or a vibrational transition, but we've also got a delta J that's equal to +1. Okay, so +1 on the left hand side, and what this means is that we're going from a J equals 0 down here at the bottom all the way up to a J equals 1. As we go to higher J numbers, okay, so here's J equals 1 at the bottom, going up to J equals 2. And you'll note, again, because I've got such a large change in vibrational energy compared to the rotational energy, I've kind of separated these by this little squiggle. So I'm basically saying there's a big gap here really between these vibrational energy levels. But what we recognize is that as we go up in J, these energy levels start to get large, right? So if you think about these energies and just look at the diagram in here, we start, how many lines do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 lines in here. We've got 11 lines in the page for the second transition, and 12 lines effectively for the third transition. So we recognize this is called the R branch, and the energies increase in size as we increase the rotational energy level that we start with. On the flip side of that, so if we go back to a color of red, okay, and so we look at this right hand side of the image, what we find is that as we in the first case, in this particular case, we're going delta J is equal to -1. And so, of course, in order to have a delta J is equal to -1, we've got to start with a J is equal to 1 in here. And so that takes us to the J equals 0 state of the first vibrational energy state. But if you just count the lines again, it's not really to scale, but we've got 1, 2, 3, 4, 5, 6, 7 lines in here for that first transition. And the second transition, we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 lines. So what basically happens in this P branch in here is that the energy of the transition decreases in size with increasing J. So let's take a look at this with all my annotations taken away. What does this mean for spectroscopy? Oh, and by the way, because the transition with delta J is equal to 0, that's forbidden according to the selection rules. What it means is we get no transition in the middle. So here's a diagram in here where I've got on the x-axis in here, I've got wave numbers. I've got no transition for, right down in here, I've got in principle delta V is equal to +1, but I've got delta J is equal to 0. So that transition is not allowed. So we don't see anything in the spectrum. This would be an infrared spectrum, FTIR measurement. We don't see anything at that middle point. But what we do start to see is we see this R branch in here and the P branch. The P branch, as I mentioned, we've got decreasing energy with increasing J. So as J increases, we effectively go to lower energies. But what we find is that with increasing J on the R branch, we actually go to higher energies. So what we effectively see are these two branches, and we'd see this. Here's our infrared spectrum. What we'd see in an infrared spectrum, if we don't zoom in, we'd see our typically it'd be the other way around. So we tend to measure it like this, but we're basically seeing this double peak in here, this double hump, if you will. That's one's the P branch and one is the R branch. So when we think about why we get this shape, again, and why we get this particular shape in here. So here's our curvature. We get some curvature to the signal. Why do we see that? There's another piece I want to introduce to you here. The intensity of any spectroscopic transition ends up being proportional to the population of the initial state. If you're familiar with Beer's law, so absorbance, remember if we go back to absorption spectroscopy, which we're not focusing on right now, but you've probably done that in lab. So absorbance, remember, is equal to some molar absorptivity multiplied by the concentration multiplied by the path length. So we know that the intensity of our transition is proportional to the concentration. It's the same idea here. So the more populated a lower energy state is, the greater the intensity of the transition. So that's the point here. I'm trying to again tie this in with spectroscopy. So I'm going to restate this. Intensity here is proportional to the population or the concentration of the initial state. So what drives the populations of our initial states? Two things. One, we're going to come across this later perhaps, but it's called the Boltzmann distribution. And basically the Boltzmann distribution says that we always, if we have any state or any system, we've got a whole bunch of different molecules in that system. What the Boltzmann distribution says is that the number of molecules tends towards a higher population in the ground state. All right, so we tend to see a larger population in the ground state, and the Boltzmann distribution actually tells us how that population changes as we increase the energy of a particular state. So that's given to us by this expression. So the energy is proportional to the population is proportional to e to the minus ej over k sub b. That's the Boltzmann constant multiplied by temperature. So for a fixed temperature, what we find is that the lower this energy level is, again, we've got a minus component in here. So that means that this exponential term is going to be larger. So when you think about it, this exponential term says that our populations are larger in the lower energy states. And as we go up, those populations start to exponentially decrease. So what that means is that we end up having a kind of an exponential drop off. I'll show you that in the next slide. What else is going on here? We've mentioned already that something called degeneracy. And degeneracy, because J can take values all the way from minus m up to plus m through 0, right? So the degeneracy increases with J. So we've got two competing factors here. Let's take a look at that in the next slide. So what this means is that if we think about this exponential term, okay, as we increase the quantum number J, that means the chances of us having a molecule in a higher state goes down. It's an exponential decay. So as J increases, so this is really an increase in J going to the right-hand side, we get an exponential drop-off. However, at the same time, we end up getting, because of our degeneracy in here, we actually get, remember the G sub j term is equal to 2j plus 1. So it's linear. As j increases, we're going to have a higher degeneracy. There's going to be more levels to populate. And so these two things go hand in hand. And what this means is effectively, if I change color again, in here it's going back to black, what I end up with is kind of a shape. It's an envelope function, right? So I multiply these two terms together and I end up getting this kind of shape that we see in the R branch and in the P branch in here. So that is the reason why we start to see certain spectral features in an infrared spectrum. So many of you will do and use infrared spectroscopy to look at and characterize different molecules that you might synthesize. And on an FTIR spectrometer, you would see these two different branches. If you look really closely with certain molecules, you're going to see the individual rotations. If it's a simple molecule like HCl, you'll see those individual transitions for the rotations. So this is a lovely little piece in the textbook that again ties quantum mechanics to spectroscopy. And this is one of those applications of quantum mechanics where we start to really understand why we see what we really see in spectroscopy. So nice little qualitative break before we start to tackle again the solution to the Schrodinger equation for that theta term. So thanks for listening.